Hi folks, welcome to our review for Calculus 1, Exam 1. Tonight we're going to be talking about limits and a little bit of continuity and intermediate value theorem. So you're going to see a variety of limits going on here. And so without further ado, we'll go ahead and get started. If you have any questions along the way, for those of you that it's your first time seeing this stuff, there should be a chat box and you should feel comfortable just asking a question at any point in time, and I will answer that question whenever it comes in. So without further ado, we can go ahead and get started. So if we have limit as x approaches 4 of x cubed minus 64 divided by x squared minus 7x plus 12, what do we do? Well, the first thing we should do is always plug in. If you plug in 4, notice you get 4 cubed minus 64, and then plug in 4 down below, you get 4 squared minus 7 times 4 plus 12. And what does this equal? Well, this equals 0 over 0. So notice when we have this, all of a sudden we end up having something that's called an indeterminate form. And what this means too, since we plugged in 4 and we have a polynomial in the numerator and denominator, it means we have a certain factor, and that factor is x minus 4. And so that's going to be useful to us because in terms of limits, what it allows us to do is we're going to be able to cancel off these x minus 4s. Now, the one down below is probably a little bit easier. It's x minus 4, and we need two numbers that multiply to 12 and add to negative 7, so that's going to be x minus 3. Some people struggle with seeing something of the form that you see in the numerator, that x cubed minus 64. Just to give you an FYI, if you have x cubed minus y cubed, what does that equal? Well, it's x minus y, and notice we're going to need an x squared. Most people think it's just x squared plus y squared, but it's not quite. It's x squared plus xy plus y squared. And notice if you multiply this out, you can multiply x times each term, and what do we get? So you get x cubed, and then positive x squared y, then positive xy squared. And then this would be negative x squared y, which would cancel off with one of those. And then this would be negative xy squared, which would cancel off with the other one. And then minus y cubed, right? So in our case, our y value is actually 4, because we have 64 is x cubed minus 4 cubed. So that should equal x minus 4, which is what we already have, x squared plus 4x. I know I'm writing it in an opposite order. X times 4 is the same as 4 times x, and then plus 4 squared. So this is x squared plus 4x plus 16. Okay. Now we had 0 over 0 originally, and so you might think it's undefined, but that, since it's both 0 in the numerator and denominator, that's an indeterminate form. And in fact, if you looked at the function, what we're going to see is it's going to be a hole, essentially, because the limit's going to exist here. And what we get, what we're left with after we cross those off, is the limit as x approaches 4 of x squared, well, I can actually drop that parentheses there as well, x squared plus 4x plus 16, and then all over x minus 3. Okay, so now we're ready to just plug in 4. And so notice this thing equals, well, we get 4 squared plus 4 times 4 plus 16 all over 4 minus 3. Well, so the denominator's just 1, and so notice you have 16 plus 16 plus 16, that's 48 divided by 1, which equals 48, and that's our final answer. Okay, so I don't know much, but what that tells us in terms of the graph, I don't know if it's increasing or decreasing just as written, but I know if here's your 4 and say 48's way up here, right? In the graph, it might be going the other direction, but you have a hole in the graph. That's what that tells you. Okay, because it's undefined when we plugged in 4 in terms of the function. Oh, and I should write, what is this? This is x cubed minus 64 over x squared minus 7x plus 12. This is equal to f of x. Okay, so I don't know the rest of the function, but I can tell you what's going to happen right around 4 by that limit. Alright, so and that's a pretty common one. Factoring, essentially, is what we use to find the limit. And you're going to use that when you have 0 over 0 and you have a polynomial in the numerator, polynomial in the denominator. In our next case, we'll plug in first. So you get 9 minus 9 over 3 minus square root of 9, which is 3. So this equals 0 over 0, once again, indeterminate form, so we're going to have to do some work. Now, some of you might see how to factor the numerator and do that this way. That can be done in this case. If not, though, and the more common thing is people get intimidated by this 3 minus square root of w, the fact that the square root of w is appearing down there. So here's a little trick that we always learn, is that there's something called basically a difference of squares, and it's a minus b times a plus b. That, notice, that gives us a squared minus b squared. So if we can take this square root of w and square it, then we'd be good. But you can't just square willy-nilly where you want. The only thing you can do is multiply by 1. And the way we multiply by 1, this is called multiplying by the conjugate. And so if we do 3 plus square root of w down below, we have to do it up above in the numerator. So notice that fraction there is 1. That's essentially what we're doing all the time with these. Anytime you see a root and there's a plus or minus sign there, you just complete in the square. So now what do we have? Well, up top we have the limit as w approaches 9 of 9 minus w times 3 plus square root of w. Okay, what happens down below? Well, notice we now have down below 3 minus square root of w and 3 plus square root of w, right? And so that should equal 3 squared minus square root of w squared. Now I could get into how the square root of w, that's when you square that, that's actually the absolute value of w, but since we're approaching positive 9, we don't have to worry about the absolute value for right now. So this becomes just 9 minus w for the sake of where our limit's approaching. And if you're worried about that absolute value, just ask a question and I'll be happy to answer what's going on there. So we have that in there. Now we're ready to kind of work the problem out. So what happens from here? Well, notice this is going to be pretty nice. The 9 minus w's cancel, and all we're left with is 3 plus square root of w. And so now we have 3 plus square root of 9 when we plug in, and that's going to be non-zero, so we get 3 plus 3, which equals 6. And that's our final answer. Okay. So now you've seen one with factoring, you've seen one with conjugation, and I mean, they follow the same suit. You're looking for, in the factoring, polynomial over polynomial, you get 0 over 0, it tells you you have a factor. In the other case, you have a square root with a plus or minus either in the numerator or in the denominator, and you're going to work with that for trying to find that answer. Now, moving to infinite limits. There's actually a very quick way to do these, and you can tell the answer extremely quick. But if you don't know that, here's the way to go about it. You always look for the degree of the numerator. So we have the limit as x approaches infinity of 7 minus 5x plus 3x squared, and we divide by the quantity 2x squared minus 4. Okay, so that whole quantity on top divided by the whole 2x squared minus 4 in the denominator. And the way to approach this one, what we actually do is we need to multiply, or there's actually some other approaches I can demonstrate if you want to see them. You multiply by the degree, and the degree of the numerator and the denominator, so I always use the one in the denominator. That's easier for us. So now how do you multiply by it? Well, you take 1 over x squared because the degree is 2. And we're going to multiply that by the whole thing. Now let's see what shakes out. So notice this becomes limit as x approaches infinity of, you get 7 over x squared minus 5 over x, because 5x over x squared just reduces to 5 over x, and then 3x squared over x squared, that becomes just 3. Then down below, when you take 2x squared over x squared, notice you're left with 2, and then when we take 4 times 1 over x squared, that's 4 over x squared. Okay? So now what happens with this? Well, each little component, you're going to take a limit. So we can move that limit. We take the limit as 7 over x squared as x goes to infinity. Well, notice if x is getting really large, that 7 really doesn't make much of a difference. That number is just getting really large in the denominator. As soon as I go to 7 over 1 million squared, I have a whole bunch of, it goes 0.00000, so on and so forth, right? So that number is getting really, really close to 0. And in fact, the limit becomes 0. In that case. So I go 0 minus, same thing with 5 over x, as x gets really large, that thing's going to 0. The 3, that's just a constant, so we'll leave that there. And then we go 2 minus 4 over x squared. Well, as x goes to infinity, that thing goes to 0. So our whole answer is 3/2. Now the easy trick to this is we could just look at the degree, and we could, as soon as you find the degree, you find the coefficients. So notice this is a +3, and this is a +2. So our answer was 3/2. That's how we found it. It's not the only way we can find it. Now, that is only in the case, I should clarify, it's only in the case when the degrees are equal in the numerator and denominator. So, for example, if the degree of the denominator is greater than the degree of the numerator, in that case, if the degree of the denominator is greater than the degree of the numerator, your limit as x approaches infinity will be 0. And then if your degree of your numerator is greater than your degree of your denominator, your limit as x approaches infinity will be either positive infinity or negative infinity. Okay? So as long as you have a polynomial over polynomial, the same rules apply all the time. Now, that wasn't the only method, though, for this, just an FYI. Some people like this better. So instead of multiplying by 1 over x squared, another way we could do this is we could factor out an x squared. So the approach would be to go this way. Factor out an x squared, so what are we left with? 7 over x squared minus 5 over x plus 3. And then if we factor out an x squared in the denominator, what are we left with? We're left with 2 minus 4 over x squared. And so notice in this case your x squareds cancel, and so just a slightly different approach. You get the limit as x approaches infinity of 7 over x squared minus 5 over x plus 3 all over 2 minus 4 over x squared. Okay? And we found that that equals 3/2 just up above. So you have two different ways to kind of approach it if you want to work it out. If you actually just learn those laws, you just, in terms of degree of the numerator, degree of the denominator, you're in pretty good shape. And you'll be all set on those. Okay, so on our next one, we have the limit as theta approaches 0 of sine squared 5 theta over theta. Now, the trig limit that we need to take note of is the limit as x approaches 0 of sine of x over x. Well, that should equal just 1. So notice, if x here we have replaced with 5 theta, so I'm going to replace x with 5 theta. So if we had 5 theta approaching 0, and we took sine of 5 theta over 5 theta, that should equal 1. But notice now, 5 theta, if that's approaching 0, that's equivalent to, so this becomes the limit as theta approaches 0 of sine of 5 theta over 5 theta. That should equal 1 as well. Okay, so we have something we can use now. My apologies. This was supposed to be a theta squared in the problem. Sorry about that. I want a theta squared, otherwise the first thing I should have done is plug in 0, and notice you get 0 for sine of 5 times 0 over 0. Now, well, we could do it if it's just theta, but it won't be as fun as what we're trying to illustrate here. So my intention was that theta squared, so we'll go with this. In terms of what happens, another way we could rewrite this is the limit as theta approaches 0 of, it's a theta, goes sine of 5 theta over theta times the limit as theta approaches 0 of sine of 5 theta over theta. Now I'm going to change this to blue just to squeeze this in here. Notice that's not quite right in terms of we need the 5 theta down below. So the way we fix this, we can't just multiply 5 theta willy-nilly, so we'll put a 5 in both the numerator and the denominator in both parts. right? Because notice 5 divided by 5 is 1. It's really our trick with these limits a lot of times, is just how do we write 1 in those cases. Now the fun part with this is we can move one 5 out in front of the limit and the other 5 in the numerator out in front of that limit. So this equals 5 times the limit as theta approaches 0 of sine of 5 theta over 5 theta. So that's our first one. Times, and we move that into the front of the other limit, 5 times the limit as theta approaches 0 of sine of 5 theta over 5 theta. So now we just talked about what that limit is. The limit as theta approaches 0 of sine of 5 theta over 5 theta, that equals 1. So you're left with 5 times 1, because we know what that limit is, then another 5 times another 1. And by the way, if we had just sine squared 5 theta over just theta, our answer would be 0 if you want to check that. It's not quite as interesting. It does happen where we're going to have stuff like that, but I want you to see some cases where it turns out to be a number that might not be intuitive. So, okay, so we get our final answer being 25 for this problem. And so now you can see those trig limits. It's basically the sine of x over x, and then you have that 1 minus cosine x all over x. That's the other one that you kind of should know about when it comes to trig limits. And basically, if you ever have a tangent or something, or secant or cosecant or cotangent, try and turn it into terms of sine and cosine early on. We'll learn some other methods later down the road, but for now, if you see that in the problem, turn it into sine and cosine. You should be pretty good. So now, our next problem, the limit as x approaches 0 of x squared arctangent of 7x plus 1 over x to the 4th minus 3x cubed. What the heck is that thing, right? So this looks kind of scary compared to the others. Don't let it scare you. In terms of, let's just draw a graph. So if you plug in, you obviously get 0 times something that's undefined, and so we have no idea what that's going to be. However, if you remember from arctangent from your inverse trig functions and stuff like that, you can recognize that arctangent is going to be bounded between negative pi over 2 and pi over 2. Okay, so with that in mind, the way we can write this is, now granted it doesn't actually equal those, but we can put them less than equal to. So our arctangent is bounded between those two values. Minus 3x cubed. And then all this is less than or equal to pi over 2. So notice we found a bound for the arctangent. Now if this was a sine, you'd bound it between negative 1 and 1. If it was a cosine, you'd bound it between negative 1 and 1. If you just have some function that's bounded between two values, you put those bounds and see what we can do. Because what we're going to try and do is squeeze this down, squeeze this function down between two parts of the function around 0. So essentially, here's what's going to happen. We're going to take a function. I'm not saying this is to scale. We're going to take a function here, and we're going to take another function. We use purple right here, and that point is what we want to show, right? Granted, our function is not as nice as this. You have 7x plus 1 over x to the 4th minus 3x cubed, so it's not this smooth curve that you're seeing right around there. But this is the idea that we're going to try and use. And so notice the missing piece of our limit is the x squared. So that's what we'll do. We'll multiply everything by x squared. So you get this, and then we have an x squared arctangent of 7x plus 1 over x to the 4th minus 3x cubed. And that's less than or equal to pi over 2 times x squared. So notice what we can do is we can toss in a limit as x approaches 0 on each of these. So what is the limit as x approaches 0 of negative pi over 2 x squared? Well, once you plug that in, you get 0. And the same thing with positive pi over 2 times x squared. If you plug in 0, you get 0. So notice that this piece in the middle has to be a number between 0 and 0. Well, the only possibility is 0. So, and we have a fancy name for this, and we're going to write it out. Limit as x approaches 0 of x squared arctangent of 7x plus 1 over x to the 4th minus 3x cubed equals 0 by the squeeze theorem. Make sure we indicate what we use there. And that's our final answer. Okay. So now we're moving on to something a little bit more challenging in terms of it's not a polynomial in the numerator, but this one's not that bad either. I will actually revert to that case where we factor out. It might look a little bit easier in those regards. So we'll factor out, but in the cases of what we're factoring out, for the numerator we're going to factor out x to the 4th. So notice we're left with a 9 minus 5 over x plus, and if you don't like this method, let me know, I can show you another method, plus 7 over x cubed minus 18 over x to the 4th. Right? And so we have that divided by, in the denominator let's factor out the x squared, and we're left with 12 minus 144 over x squared. Okay? So notice that this equals the limit as x approaches infinity of, well, you could rewrite the numerator as the square root of x to the 4th times the square root of all that junk, 9 minus 5 over x plus 7 over x cubed minus 18 over x to the 4th, and all that's divided by x squared times 12 minus 144 over x squared. Now, an easier way for us to write that, x to the 4th, if you take a square root of x to the 4th, notice you're left with just an x squared. Questions on that part? Because a square root is just raised to the 1/2 power. So what happens is, oops, I forgot to close off that parentheses. When you take a x to the 4th to the 1/2 power, you take 4 times 1/2, and that gives you 2. That's where that comes from. And so now our x squareds will cancel, and we're left with a decent limit for us to look at. This is the square root of 9 minus 5 over x plus 7 over x cubed minus 18 over x to the 4th. And then all that is over just 12 minus 144 over x squared. Now, any time we have an x in the denominator and just a constant in the numerator, there's a theorem in your book, or a fact, or whatever you want to call it, that states that that's going to 0. So the pieces that are going to 0 are this piece, this piece, and this piece, and this piece. All those are going to 0. So what you're left with is the square root of 9 minus 0 plus 0 minus 0. And down below you're left with 12 minus 0. So notice that makes us have square root of 9 over 12, which is 3 over 12, which reduces to 1/4. By the way, notice at any point in time I have not used a calculator at all. So all these are just algebraic manipulations, okay, and that's what we're going to be doing over and over and over again. Okay, so now you've seen quite a few. Let's change gears here slightly, and let's switch to continuity for a few seconds. So for what values of the constant c is the function f of x equals this piecewise function where you have cx squared plus 4c if x is less than 3, and then c squared x if x is greater than or equal to 3. We want that function to be continuous on negative infinity to positive infinity. Notice you basically have a polynomial where c is just some constant. So you have polynomial and a polynomial. What we need to do, so here's what happens sometimes. Sometimes you'll have something like, and so notice our magical number is 3, and so you have, well, both of these are actually linear, so I'll draw them as such. So you could have something like this, and you could have something where these line up. So you could have another case where you have this piece over on here, here's 3, and then all of a sudden this lines up. I'm not saying it'll make a perfect line, but it gives you an idea as to what could happen. So those are some of the scenarios that we're looking to see. Now notice I put down 3, and there's a reason for that. Why 3? Well, notice the break-off point is at 3. So the only part we need to check is, first we need the limit as x approaches 3 from the left of f of x to equal the limit as x approaches 3 from the right of f of x. And from there you can determine too, you need the limit as x approaches 3 of f of x to equal f of 3. So this would be what we need for continuity at x equals 3. Okay. So the limit as x approaches 3 from the left of f of x, well, what is that? That's just the limit as x approaches 3 from the left. And the reason we need a left and right limit to be equal, because that's the only way the limit as x approaches 3 is defined. So limit as x approaches 3 from the left, so this would be the numbers less than 3. So notice that's our first case. So this is cx squared plus 4c. So this should equal the limit as x approaches 3 from the right of, well, 3 from the right would be our case where we're greater than or equal to 3, and so, or just greater than 3. So that would be c squared x. Now what do we do? Well, notice we're taking x and approaching 3, so all we need to do now is plug in 3 for the x. So c times 3 squared plus 4c should equal c squared times 3. So notice this makes what? Well, this is 9c plus 4c, so you get 13c equals 3c squared. Okay, so in order for a limit to exist, here's what we'll do. We'll get everything over to one side. 0 equals 3c squared minus 13c. And so we can factor out a c. So you get 0 equals c times 3c minus 13. And the way to solve this, you set c equal to 0 for each factor, or each factor that you have up here equal to 0. So you get c equals 0, and then you get 3c minus 13 equals 0. So notice this is c equals 13 over 3. The way you can get that, first add 13 to both sides, then divide both sides by 3. And we have c equals 0. So for what values is this continuous? Well, notice now we already had the equality included with the right hand limit, so that part was already taken care of for the f of 3. We know that it's going to work, and the limit as x approaches 3 is only a possibility at those values, c equals 0 and c equals 13 over 3. So the answer to this is when c equals either 0 or 13 over 3. Or actually not equal. C is an element of, I should say. Oh, either way. So if you put equals, I'm not going to harm you on that, but I'm just writing element of just for kicks. So hopefully that makes sense in terms of what's going on there. I don't see any questions at this point, but hopefully you can see you're doing a left-hand limit and right-hand limit, setting those limits equal to each other when it comes down to it. So now, taking that to a graph side of things, for the function f, graph below, find the following limits. And so we have the limit as x approaches -5 from the left. And so what the heck does that look like? Well, so what we'll have to do, you see each of these is 1. This is -1, -2, -3. I'll mark that because that's going to come into play in a second. -4, and -5 right here. So we want to check out the y value as we're approaching from the left. So notice on the left hand side of 5, so if I draw a 5, and make sure you make that sound effect when you draw a -5. If I'm on the left hand side, I'd have to be over on this side of things. So I want to get the graph on that side, and so notice I'm going up and up and up and up and up, right? So that keeps on going up. That means we're going to positive infinity when we're on the left hand side. If you look on the right hand side, notice we're going to, well, the right hand side of negative 5 looks like it's going down and down and down, so that's going to be negative infinity. So now our limit as x approaches negative 3, we're going to still draw our negative 3 value. Okay, so in this case, notice from the left hand side we have positive infinity as our limit. From the right hand side we have positive infinity. Since both of those match up, they aren't going in different directions. The answer is positive infinity. Keep that in mind though, just a little FYI. Limit as x approaches negative 5 of f of x. Since it goes to infinity and negative infinity, that's a does not exist situation. So just want you to see that and what's going on there. Now our limit as x approaches positive infinity, we're looking for the y value that we're approaching as we take this thing out further and further this way. Okay, so notice that y value, we've gone down negative 1, and then negative 2 is the value it seems to be getting closer and closer to. So our y value is negative 2, and that's all this is. When you see an infinite limit, it's just a horizontal asymptote. So just a little comment, you have a horizontal asymptote at y equals negative 2. And notice our other, it doesn't seem like it's a horizontal asymptote because it's crossing, but notice this thing's getting, the oscillations are getting less and less. So this part, as we go towards negative infinity, that's approaching when y equals positive 2. So we also have that horizontal asymptote at y equals 2. Wowzers, right? So other, just an FYI, other types of things that you'd have to look out for is when you have what's called a jump discontinuity. So you have something like that. That's called a jump discontinuity. You only will have left and right hand limits in that case. You will not have a limit exist from the for the number whatever point is here. The other scenario where you will have a left and right hand limit and the regular limit is when we have a hole in the graph. Okay, so you will actually get a value for those cases. But so right here, I had some people ask about infinite discontinuities. I wanted to make sure those were touched on. But make sure you're also aware of jump discontinuities limits when you see a graph, and then also the holes as well. If you have questions on those, please ask. That's what I'm here for. So now the other question, determine the intervals of continuity for f. So this part seems pretty tricky, but it's actually not too bad. You're just looking where the graph breaks off. So notice we go from negative infinity. Once we get to negative 5, we have an infinite discontinuity. So we'll put negative 5 and we'll put up parentheses. And then we still don't include negative 5, so that's why the parentheses is there. And then we jump all the way to negative 3. We're smooth until we get to negative 3. There's another infinite discontinuity. And so once again, we'll pick back up at negative 3. And then we go on all the way to infinity, and there's no other points that are troublesome. So in terms of the intervals, all you're doing is just putting the parentheses where that discontinuity occurs. The only difference would be is if you have a scenario where maybe there's a whole range of values where it's discontinuous. That can happen as well at times. We won't see too many of those in this class though. So now, moving forward, does there exist a number that is exactly 1 more than its cube? Justify your answer. What the heck is this all about, right? So we've done continuity, we've done limits. What the heck's going on here? Well, let's see if I can put this in the screen a little better. Hopefully y'all can see that pretty well. Alright, so does there exist a number that is exactly 1 more than its cube? So first off, let x be a possible solution. Usually we shouldn't assume that there's a solution, but let's say there is a possible one. Then what you'd have is x cubed plus 1, right? 1 more than its cube, right? Exactly 1 more than its cube. So that means x cubed plus 1 should equal x. Now, subtract x from both sides. So if you look, we can create a new function. So this implies, right, that x cubed plus 1 minus x equals 0. Right? So now, let f of x equal x cubed plus 1 minus x. Now, we want to try and find a value where there's a solution to this, so where it equals 0. that might be hard, right? A lot of us don't know how to factor cubics or anything like that. So what's the fixer for this, right? And the fixer is we can actually try and find an interval where we have our plugged in values be on either side of 0, and then we know that 0 must be a solution. And the theorem that kind of comes to the rescue here is the intermediate value theorem. So first off, in order to use the intermediate value theorem, you need to recognize that this is a continuous function. So notice f is continuous, and the reason why it's continuous is a polynomial. And we know that all polynomials are continuous. So since it is a polynomial, okay, so now we need to find things on either side of 0 if possible. So notice now, let's consider here, we'll do two values. Try and keep this easy on ourselves. We'll plug in f of 0. So notice if we plug in f of 0, we get what should we have here? So f of 0 would be 0 cubed plus 1 minus 0, and so that would equal positive 1. Now we need a number, if things are to work out and give us this 0 as a solution. When I'm referring to 0, I'm referring to this 0. And actually, just to make sure, what I'll do is I'll change this just slightly. I don't want you to get confused on the zeros, and it wasn't necessary for me to use that number. So I'll plug in negative 1. So notice if we go negative 1 cubed plus 1 minus a negative 1, what do we get? So you'll get negative 1 plus 1, which is 0, then minus a negative 1, which is positive 1 as well. Alright, so this will do the trick for us and still get us at the answer. I want to make sure that we're aware of what's going on here. And then the other case, so now we need to plug in some numbers. So notice both of those, if I did 0 and 1, and 0 and negative 1, that wouldn't have done anything for us because we haven't been on either side of 0. However, if I plug in negative 2, I think that will do the trick for us. We get negative 2 cubed plus 1 minus negative 2, and I apologize for the crying in the background. My son does not want to go to bed right now. So we have negative 8 plus 3, and so that should be negative 5. Okay, so that's what this says. Now, just an FYI, I have no idea what this graph looks like. That's kind of a lie. I do have a pretty good idea what this graph looks like, but that's for other reasons. If I'm taking calculus for the first time, I might have no idea what the graph looks like. But I do know at negative 2, I have this value of negative 5, right? And then I know at negative 1, I'm going to have this value of 1. So I have these 2 points, right? And so what happens is I have to connect these with a smooth line. Now I could have all sorts, I'm not saying it looks like this, but say I have all sorts of this stuff going on here. Sooner or later, I'm going to have to cross that x-axis. That's what the intermediate value theorem states. So somewhere in that interval, I'm going to cross that x-axis. So what does this relate to? So by the intermediate value theorem, and we can apply it because it's a continuous function. If it's not continuous, this does not apply. There exists a C in the interval. Now what interval should the C occur? So what happens is they're saying, hey, this value right here is C, right? The x value. There exists a C in the interval, and our interval goes from negative 2 to negative 1 in this case. Such that, what happens? Well, when you plug in C into F, right, what would happen? Well, notice this coordinate, that would be C comma 0. Right? So that means f of C equals 0. So does there exist a number? Well, notice we just found, hey, by the intermediate value theorem, there has to exist a number in this interval. Therefore, there exists a number that is exactly 1 more than its cube. Now the funny part is, notice we didn't find that number. Yeah, it's between -2 and -1, and we can use a bisection method and kind of cut it down and get those intervals smaller and smaller. But at the end of the day, we don't need a solution to the exact value. We just wanted to find out, does a solution exist? And we have that existence here. Okay. Questions on that? Those are usually pretty tricky arguments, but once you get the hang of them, it works out pretty nicely. So now we have infinite limits of a different type. I'm going to try and show you on these and just to beware on some things too. So limit as x approaches 2 from the left of 7 over 3x minus 6 cubed. So first off, when we take a look at this, what's actually happening? Well, the 7 over 3x minus 6 cubed, when we plug in, we get 7 over 0 cubed. So this is 7 over 0 cubed. This is not, it's not an indeterminate form. So actually what's going to happen is you're going to have a few cases. You can have either infinity, negative infinity, or undefined. Okay? So now what we need to figure out is, okay, if we have 3x minus 6 going on, when we have a number x less than 2, what's going to happen to this? Well, is it going to be greater than 0 or is it going to be less than 0? Well, if you have less than 2, you plug in a number like 1.9. So 3 times 1.9, notice that's going to be some number slightly less than 6, so that means this is going to be less than 0. So what that means is this thing is negative. So you have 7, and this is approaching 0 from the negative side, so if you get 0 on a negative side, notice you're going, no, I should do it on the side of 2, to be honest with you. So if I have 2 right here, what happens is you get something that goes like this. So this thing equals negative infinity. Versus on the other side, if you go from the right, it's going to be positive infinity. Okay, why is it positive infinity? Well, notice if I go greater than 2, that's a number like 2.1, 2.001. All those are numbers slightly greater than 6, so that you'll get greater than 0 in those cases. Okay. Now you might be saying, okay, so you did positive infinity and negative infinity for these. What the heck, when's the does not exist scenario come into play? Well, when you have limit as x approaches 2, notice you're approaching negative infinity from one side, positive infinity from the other. So this thing is a does not exist. Okay, so we plugged it in, we came up with 7 over 0, found out, oh, we got a problem there, and that's the fixer, right? So we got negative infinity for the limit from the left, and I'll even write down, just for kicks, so you can see it. Limit as x approaches 2 from the right of 7 over 3x minus 6 cubed equals positive infinity, right? So that's why we had does not exist, because the left-hand limit and the right-hand limits do not match up. That's a plus, not a 7. So, all right. So now, what about limit as x approaches 0 of secant squared of x? So some people might struggle with secant. And I'll tell you the fixer for that real quick is write it as a cosine. So this is just 1 over cosine squared of x. Okay, because secant, oh, and if you don't know, it's time to know, you're going to learn that secant of x equals 1 over cosine x. So if I'm squaring secant, I just square, if I square the 1, you get 1 again. And so this is just 1 over cosine squared of x. Okay, so now we want to do the limit as x approaches 0 from the right. Well, notice, if we plug in cosine of 0, that equals 1. So a lot of people get infinite limit happy. This is 1 over 1, so this one's just a plug-in. And we get 1 as our solution. However, if you look at this case, this is the limit as x approaches pi over 2 of 1 over cosine squared of x. And so notice if we go 1 over cosine squared of pi over 2, we'd get 1 over 0. That's a big no-no, right? So we're either going to be approaching infinity and negative infinity from either side, and then get a does not exist scenario, or get an infinity as a solution or a negative infinity as a solution. Well, this one's actually kind of easy, because notice we're squaring the cosine. So we're getting 0 and we're squaring that. So the only possibility is positive, on the positive side of 0, right? Because we can't be negative if we have a square down below. So that means since we have 1 over 0 and this is positive, this whole thing, if you go 1 over, and if you don't believe me, what I'd suggest, even though we can't use calculators on the exam, if you don't think this thing is going towards infinity, so notice we're getting closer and closer to 0, right? Plug in a number like that and see what happens, right? Remember, this is 1 over, I don't know, how many zeros did I put in? Like, so a quintillion worth. So 1 divided by a quintillion in the denominator, that becomes a quintillion, right? So we're getting larger and larger with our numbers. So this thing is blowing up towards infinity. Okay. Hopefully that makes sense, and you can see how squares, that can turn this thing to positive infinity. If you notice you have an odd power down below of some sort, that's usually the case where you can get a split on negative infinity and positive infinity. It will depend upon what's in the numerator, but for right now, just constants, so nothing too cumbersome there. And also we saw some trig functions too. That's always good. So now, the next question, determine if the following function is continuous. So in order to do that, first we need to check the left-hand limit and the right-hand limit, right? Because we need to see if the limit exists. So we need to do the limit as x approaches 1 from the left of f of x, and we'll need to check it with the limit as x approaches 1 from the right of f of x, right? Whoop. So the limit as x approaches 1 from the left, that would be when x is less than 1. So notice that's this case, this top case. So that becomes 5x minus 7. So just plug in 1. So 5 times 1 minus 7. And that equals negative 2. Now our next case, limit as x approaches 1 from the right, that would be where we have greater than. So this would be x squared minus 3 is the function that we're going to look at. So notice we'll plug in 1. We'll get 1 squared minus 3, and this actually gives us a value. It's negative 2. Notice the left-hand limit and the right-hand limit are equal. So you get the limit as x approaches 1 of f of x equals negative 2. So we have a solution there. Now, we need to compare this to f of 1. But f of 1 we get by looking at this value. So because x equals 1 there, so notice our f of 1 equals negative 5. Okay, but these two aren't equal. So that tells us something. Since the limit as x approaches 1 of f of x does not equal f of 1, the function is not continuous. At x equals 1. And there's your result right there. Okay. 1 was the only part we really had to check because those were the 3 breakoff points. I mean, the 3 functions just dealt with 1. Now, if I had a 2 in 2 of the places and a 4 in 2 of the places, then I'd have to check multiple values. But notice we found right there, it's not continuous, so the function can't be continuous overall. And, oh, if you're wondering what happens, what does this look like? Okay, so in terms of the graph, let's see, x squared minus 3. Okay, so as we're at 1, so you get something like this, and then 5x minus 7, so you'll be going there. So you get a hole in the graph, and then at 1 you get negative 5. So let's say negative 3, negative 4, negative 5. So we'll say negative 5 right here. Okay, it's going to look something in the ballpark of that vicinity. Okay. Questions on that one? Okay, so just showing you how you can get a hole in the graph. That's one way. The other way is if you have a fraction where it turns to 0 in the numerator and denominator, those ones that we did factoring on. That was a good example for our limit. So here's one that's kind of different. So we have limit as x approaches infinity. You may not be aware of what's going on here. So if you take a look at this, another way to write e to the negative x is 1 over e to the x, right? That's just properties of negative exponents. So this is 1 over e to the x over x to the 7th. And notice we can even bring that e to the x on down. And that's important, because notice we now have 1 over e to the x, and we have an x to the 7th down below. So when we plug in infinity, you have a constant. That constant's 1. And this thing down below, notice we plug in numbers, and we're just getting larger and larger and larger in the denominator. So that means this whole thing is going to 0. Okay? When you have a constant and you have something going to infinity in the denominator, that whole limit goes to 0. Now, if you take a look at this one, the sine squared of x, let's see what happens. If we do sine of 0, sine of pi, sine of 2 pi, so on and so forth, right? So I can do any sine of n pi, right? Notice all that we're getting on all these, 0, 0, 0, 0. However, oh, I'm sorry, I did the positive direction. We want to go towards negative infinity. If I put negative n pi, negative pi, so on and so forth, same song and dance. Now on the other case, if I do sine of negative pi over 2, sine of negative 3 pi over 2. Oh, and each of these I can square them. It's not going to make a difference. Sine squared of negative 5 pi over 2. And then let's make this sine squared of negative k pi over 2, where k is odd. Notice this gives us 1, 1, 1, 1. Notice one of these is going to 0, and notice we're going to negative infinity, the negative n pi. The other one is going to 1, where we're going to negative k pi over 2, where k is some odd integer. So this has, we're taking limits in two different directions, right, as we're approaching negative infinity. That's impossible. Remember, it has to converge towards the same number all the time. So that means that this is a does not exist scenario. Now you keep that in mind, because you look at the next one, you might say, okay, so that's a does not exist. Well, no. And the reason why here our game changes a little bit, first off, you can do negative 1 is less than or equal to cosine x is less than or equal to 1. Now we can make that by multiplying everything by x squared plus 1 over x squared plus 7. So we get negative 1 over x squared plus 7 is less than or equal to cosine x over x squared plus 7. And that's less than or equal to 1 over x squared plus 7. Okay. So now if we take a limit as x approaches infinity in this case, in each spot, notice we have a constant on the left, and we're dividing by x squared plus 7 as x goes to infinity. That thing's going to 0. So we get 0 is less than or equal to that limit as x approaches infinity of cosine x over x squared plus 7. And that thing's less than or equal to, notice when we go 1 over x squared plus 7 as x goes to infinity, that's equal to 0 as well on the right hand side. So this means our limit as x approaches infinity of cosine x over x squared plus 7 equals 0, and now you've seen it in a slightly different manner by the squeeze theorem. Oh, the squeeze theorem. So, giving you an idea of some of the different problems lurking out there, right? What else is out there? Now, this will not be on your exam, by the way. I did not put any delta epsilon on this exam 1. But I'll give you an idea of how these things go. So notice that limit as x approaches 5 of 4x minus 7 equals 13. If f of x equals 4x minus 7, find a value for delta in terms of epsilon, which is greater than 0, such that whenever the absolute value of x minus 5 is less than delta, we find absolute value of f of x minus 13 is less than epsilon. So here's the whole idea. In general terms, let's say you have some function, right? We'll draw the function. Who cares what it looks like? This one's obviously linear, so it's not going to be that bad. But say you have some point. We have c, and we have f of c. Well, what we say, in order to find this f of c, maybe we have this range, right? That we know that we might be slightly off with our target, but we want to be within a certain range. And the range that we're looking at is this f of c minus epsilon and f of c plus epsilon. And so what happens is we end up going down below and seeing what do we have to keep our c values within on each side to keep it consistent. Now we want to choose delta that stays within this band here. And remember, we want to be equidistant on either side, so we create this c minus delta and c plus delta. But the trick is we want to keep it usually in terms of epsilon, right? Because epsilon can range to whatever number we want, so we try and keep it within that certain range. But as long as this interval, and so now notice if I take this band on up, it's going to fit inside that set of y values. That's the whole goal of this, right? Just to fit inside. So we'll usually come up with numbers that are exact to one of the endpoints, but you could go even further inside. Keep that in mind, okay? So let's see this at work. So let's assume we start with f of x minus 13 is less than epsilon, right? So what the heck is f of x? We want to pull an absolute value of x minus 5 in terms of epsilon somehow, some way. So f of x is just 4x minus 7, and then minus 13. Okay, that's less than epsilon. So can we get this factor out of here? Well, yeah, it's not that bad. You get 4x minus 20 is less than epsilon, and that means the absolute, don't let your eyes fool you, that's an absolute value of 4x minus 20. Let me try and make sure, just to distinguish that you aren't seeing ones there. Absolute value. Okay, so absolute value of 4 times the quantity x minus 5 is less than epsilon. So in our case, what we have, notice 4 is that's a positive constant, so we can pull it out in front of the absolute value. It shouldn't play any extra role there. So we get 4 times the absolute value of x minus 5 is less than epsilon. And so that means if we wanted to solve for the absolute value of x minus 5, notice that has to be less than epsilon over 4. So if we want to be within that band, what we're trying to get is we're just going to choose delta to equal epsilon over 4. Now sometimes you have to go back and rewrite a proof, but that's the whole trick to these problems, is trying to figure out what the heck is delta. And the way you do it is whatever this value is down below, you want to find the absolute value of x minus that value in terms of one of the factors of f of x minus the final limit, right? That's all there is to it. And that happens over and over and over again. Any questions on that? Okay, so I don't see any questions. I wish you all the best of luck then coming up on the exam. Hopefully all goes well. If you do have any questions in the meantime, you can shoot me an email or